Hello, my name is Robin Mitchell and welcome to this episode for Electromaker. In today's video, we are going to learn how we can reduce the power of our hardware embedded projects using various different circuit techniques and software techniques, and then we will monitor the effect of these techniques using the Power Profiler Kit 2 from Nordic Semiconductor. So before we can jump into the circuit theory of how we can reduce the power in our projects, we first need to know what the Power Profiler Kit 2 actually is, what it can do, and how it can be used in our projects. So to start, the Power Profiler Kit 2 is an ammeter at the very core of it. It can be used to measure currents up to 1 amp, down to a resolution, I believe, of about 200 nanoamps. And this can allow us to also monitor the power because it not only allows us to measure the current, it can also provide a voltage. Now, the device is powered from 2 different USB ports depending on the current that you want to provide. If the current that you need is sort of around the 200 to 300 milliamp range, then you only need to use the 1 USB port. If you're looking to really push it up to the amp, then you will need to use the 2 ports provided. Now, not only does the Power Profiler Kit 2 allow you to read the current in real time as well as the power and provide a voltage either from the device or externally, it also has an 8-channel input logic port, essentially a logic analyzer. Now, this is particularly useful in scenarios where you may have a complex circuit with various logic inputs and outputs, and you want to see how those behave under different power scenarios. So for example, you might have a microcontroller who has an input port, and this input port is used to wake the microcontroller up from a deep sleep. But you're not quite sure if it's working correctly, so what you can do is use this logic analyzer with your microcontroller and monitor the power at the same time, and you can confirm if that pin is working, because if there is a detected pulse on that pin, you would expect the current consumption to suddenly increase as it wakes up from deep sleep. So overall, the PPK2 provides your circuit with a voltage, or it can provide voltage from an external source. It can monitor the current going into your project and then infer the power consumed, and it can also provide an 8-channel input logic analyzer for rather complex projects. So now that we know what the PPK2 is, it's time to look at a bit of circuit theory so we can learn how we can reduce the power of our projects. Now, when it comes to power consumption, there are 2 main categories. They are static power and dynamic power. Static power is power consumed by a device by just being on or running, whereas dynamic power is a little bit more complicated and involves power that's consumed during a switch of some kind, and we'll just look at that a bit later. So let's look at some examples of static power. A potential divider is an excellent example. The thing is always running so long as there's a voltage. It will always consume a set amount of current, and that is static power, with the current and the voltage being multiplied together to give you the total power consumed. Another great example of static power would be something like a linear regulator. The 7805 is one that comes to mind and is a very popular one amongst makers. Simply put, the 7805 takes an input voltage and provides an output voltage that's fixed. So for example, you can put in 12 volts and you'll get something like 5 volts out for the 7805. Now, the static power consumed in that circuit would be whatever the regulator is dumping out to try and maintain that 5 volts. So for example, let's say we have a circuit connected to the 7805 that needs the 5 volts and is consuming 100 milliamps. The voltage difference that's between the 12 volts and the 5 volts is 7 volts, and that's what the 7805 essentially has to dump. Now, it has to do this at 100 milliamps, so you end up finding that the amount of power that's being dissipated by the 7805 is 7 volts times by 100 milliamps. That gives you about 0.7 watts. So now let's take a look at the second category of power consumption, dynamic power. Dynamic power essentially is the power consumed by a circuit when it's in operation, but it's doing something. And generally speaking, this is when something switches. So for example, CMOS logic gates are an excellent example of dynamic power consumption. When a CMOS logic gate, say a NOT gate, isn't switching and it's staying at its value, say you've got a NOT gate, 1 going in, 0 coming out, it will consume some static power. But the moment you switch the input from a 1 to a 0, the whole thing changes, and it's in that instantaneous change that power is consumed, a bit of extra power, and that is called dynamic power. Now, the reason why power is being consumed in that example is because if you look at the construction of a NOT gate, you have a P-type and an N-type, and the moment that they switch, both of those transistors are briefly on. And so current can flow through the P, through the N, and into ground, and that can be a large amount of current, surprisingly. So when you look at a CPU in a modern computer, which is almost always made from CMOS logic, you'll find that if it wasn't clocking, it probably wouldn't consume much power at all, probably nothing. The moment you start clocking into the gigahertz, that's when your AMD processor becomes a toaster. Now, even though static and dynamic are the two main proper types of power consumption, I also like to throw in two more, and these are leakage and waste. Now, an example of a leakage power consumption would be something like a reverse bias diode. It's not supposed to conduct when it's in reverse bias mode, but there is a small amount of current that goes backwards, and that results in a small amount of power consumption. Now, an example of waste power consumption is basically any device or circuit that's consuming power unnecessarily. So the 7805 linear regulator wastes a lot of power to bring the 12 volts to 5 volts, but I don't think that's a fair example of wastage, because you need to drop that power in order to get that voltage, because it's a linear regulator. So what I believe to be a really good example of wasted power is a potential divider circuit, or one that's been designed poorly. Now, for example, you could design one that needs to divide a voltage by 10, and you could use a 100 ohm resistor in series with a 980 ohm resistor to give you about that sort of 10 division. Now, that would work, but it would also consume a lot of current. You could achieve the same result using a 10 kilo ohm resistor and a 98 kilo ohm resistor. They would both divide the voltage by 10. Now, of course, that does depend on the circuit that needs to read that voltage, because if the circuit that's going to connect to your potential divider has a low input resistance, then you're going to need to have a low resistance potential divider. But if it's something like a microcontroller input port for an ADC, you could definitely get away with a much higher resistance on your potential divider. And that way you could save a significant amount of power. So now that we know what the main types of power consumption are, we can now use this to understand how we can reduce the power in our circuits. So let's see what the top tips are. So the first and probably the most important rule is to use a switch mode power supply whenever you can. Compared to a linear regulator, they are insanely efficient, easily to the 95 to 98 sort of percent area, depending on the design. Of course, microcontrollers generally need to have a linear regulator input because it's just so much smoother and it hasn't got the switching noise, but if you can get away with it, use a switching mode power supply circuit. The second most important tip is to always use the biggest resistors you can. Simply put, the bigger the resistor, the smaller the current, the smaller the power consumption. That includes potential dividers, pull-up pins, and those that provide current to, say, something like an LED. Especially LEDs, actually. Even though an LED could operate, say, at a theoretical 20 milliamps, you can usually get away with a 5 or a 4. So making those series resistors bigger is a great way to save power. The third top tip for reducing power in your projects is to turn off sensors and disable peripherals when they're not needed. You might have a project with different sensors externally connected to your microcontroller, and they might have enable pins, and you should take advantage of that to turn them off when they're not needed, as that can significantly reduce static power. Additionally, microcontrollers also contain a bunch of peripherals that might be very good for different projects, but you may not be using them in yours, and they also consume static power. So again, turn off all peripherals that you don't need. Another good tip is to remove circuitry that's not needed. When you're in the prototyping stage of a project, say you're using something like the ESP32, you may have a lot of external devices on that project that you don't need. It could be something like a serial converter to a USB. It could be something like an external memory chip. It could be another sensor. And if your prototyping stage can get away with it, that's great. But if you're trying to bring that into a final product and you want to reduce that power as much as you can, get rid of any circuitry that you don't absolutely need, as any circuitry consumes static power, and that is something you want to target. Now, when it comes to microcontrollers, another extremely useful tip for reducing the amount of power consumed is to reduce the voltage at which it operates at. Higher voltage operation tends to see higher current consumption, and that is just something you absolutely need to target. So if you've designed an IoT sensor or a Bluetooth sensor and you're using 5 volts, you've got to be going down to at least 3.3, if not further. In fact, a lot of microcontrollers can go all the way down to the 1.8 volt range, and that can significantly reduce power consumption. On the topic of microcontrollers, another great tip is to reduce the core frequency as much as you can. Sure, it's great if your device is operating at 300 megahertz and you're able to kick out a bunch of processing power, but if you're creating something that needs to conserve power and run on a battery or something, then reducing that core frequency can make a massive impact, and we will see that later as we experiment with the PIC18 where we drop its core frequency from, say, 16 megahertz to 1 megahertz, and you see the power consumption just massively drop. So yes, reduce the core frequency as much as you can. And finally, and probably the most important tip for anyone with a microcontroller who wants to reduce power, explore sleep modes. Most microcontrollers will have the ability to go to sleep, and what that will do is it will shut down its internal clock, it will shut down onboard peripherals, and when it does that, the power consumption can almost go down to the nanoamps. I believe the PIC18 has the ability to go down to something like 20 nanoamps or 22 nanoamps, and that is an insane amount of minuscule current. That's ridiculously small, and the moment you do that, your device is almost consuming no power. So sleep modes are really, really useful to explore. So in this first example, we're going to observe how clock speed affects power consumption in a microcontroller. Now in this setup, we have a PIC18 chip, we have an LED connected to port C, we have a switch which is connected to port B, but those two aren't going to be used until the next example where we look at sleep. So here we have the power profiler kit 2 providing power to the PIC via the PIC kit 3. So the power comes out of the programmer, goes into the power profiler, and then comes onto our board. So we can measure the current while it operates. So if we now go over to the code, what we can see is an extremely basic example. All we're doing in this code is when the microcontroller turns on, we set the oscillator to a specific speed, and then we do an infinite loop with a delay. Now the three options that we're going to be testing are high speed, medium speed, and low speed of around 16 megahertz, 1 megahertz, and 32 kilohertz respectively. So if we go ahead and run this example, and then head over to the Connect for Desktop Power Profiler, we can click Start once our device is programmed and running, which it is now. So we go ahead and click Start, and as we can see, we are having an average current consumption of around 1 milliamp. But now let's observe what happens when we increase the clock speed to the highest speed setting, which is 16 megahertz. So we go ahead and copy that in, save, program, wait for the program to complete. So before we were consuming around 1 milliamp, but if we now start the data logger, we can now see that we're doing around 4 milliamps, about 3.8. So by increasing the speed from 1 megahertz to 16 megahertz, we've gone from a current consumption of around 1 milliamp to now around 4. Now let's observe the current when we drop it to a low speed of around 32 kilohertz. So before we were getting around 4 milliamps, if we now run it, you can see that we are consuming an incredibly small amount of power, only around 100 microamps on average. And we can even zoom in to see how different portions of the code produce different results. And now let's really push this microcontroller to its limits. Not only are we going to use the highest clock speed setting, we're also going to enable the PLL, which will multiply that clock by 4. So we go OSC bits, and it's PLL enable, and we're going to go 1, and we're going to go ahead and program that, and then observe the current consumption. So previously when we were running this example, at 60 megahertz, we were looking at a current consumption of around 4 milliamps. But let's see what it looks like now. Well, as we can see now, we're averaging around 13 milliamps, which is significantly more than what we were consuming before. So in the previous clock examples, we were using a voltage of 5 volts. But let's see what happens now when we drop the voltage from 5 to 2.5 volts. Previously, we were consuming around 13 milliamps on average, but if we now start this, what we see is a reduced current of 9.23 milliamps. So it can be seen that by dropping the voltage from 5 volts to 2.5 volts, our current consumption has gone from around 13 milliamps to 9.23 milliamps. and that is still operating at the same CPU frequency with the PLL enabled. The next example here is we're going to observe the power consumption differences on a microcontroller when you turn peripherals on and off. Again, the code is very simple, and all we're doing is turning on 3 different peripherals, having a delay, and then turning them back off. Now, because all peripherals have a static power consumption, what we should observe is more current consumption during this portion of the code and less current consumption during this portion of the code. So using the PPK2, let's observe the current pattern on this program. So in this live view, what we can see is the average current changing quite dramatically. If we just stop the current view, the currents change from around 730 microamps to 973 microamps, which is about a 200 microamp difference. Now, you may not think this is much, but in the long game, this can have a really big impact over long periods of time. And this is a really good example of why turning off peripherals that you don't need is a great way to reduce power consumption. Now, in this example, we're going to look at how sleep mode affects current consumption. In this example, when we push the button, the device will come out of sleep mode. It will flash the LED on 5 times, and then it'll go back into sleep mode. And if we go into the code here, it may look a bit complicated, but it's actually very simple, and most of this is just configuring the device. This section of code here is just an interrupt. So when it detects the press of a button, it will clear the interrupt flag. It's also important to note that the button is connected to RB0, which is your interrupt 0 pin. And this is what is used to actually wake up the microcontroller from sleep. Just like before, the main code configures the oscillator to run at its highest speed. We enter the sleep instruction. We enter sleep when executing the sleep instruction. This one's quite important. If it's set to 1, it will just idle instead, which does not save power. We configure the interrupt here so that when we do push the button, it jumps to this piece of code here. This is just configuring the different input-output ports. It's not entirely important. It is needed, but its function isn't important to the sleep itself. And then we have this while one loop, which is just an infinite loop, and all we do is flash the LED 5 times, turn off the LED to save power, and then enter sleep mode. So let's see how that looks on the Nordic Power Profiling app. So we go ahead and run start, and right now the microcontroller is in sleep mode and is averaging around 41 microamps. We push the button, get the LED flashing, and now it stops and it's back into sleep. And it's quite cool because not only do we get the live view, but we can see all the different stages of power consumption during that program cycle. We start off at sleep mode, we push the button which initiates the microcontroller, it then executes our loop 5 times, and this is the current consumption of the LED here, and this is the current consumption normally when the program runs, and then it comes into sleep mode, back into a low current consumption mode. And if we consider the amount of current being consumed during this period compared to when it was on, even with the LED off, which is around here, so as we can see, we were able to drop the current consumption from around 4 milliamps down to around 200 to 300 microamps, which is a lot of power saved. Now, just to demonstrate how effective sleep modes are, in this example, we're using the ESP32. And if we go into the Arduino IDE, we can load up this basic timer wake up example. And you can find this from File, Examples, ESP32, Deep Sleep, Timer Wake Up. Now what this program does is every few seconds the device wakes up, sends some messages out over the UART port, and then goes to sleep. So we're not going to observe the messages coming from the ESP32 because they're not important. However, what we will be observing is the current draw during this time when it goes to sleep, when it comes back awake and tries to send some stuff to us. So if we head over to the power profiler, we can go ahead and click enable output. That will boot the ESP32. And if we observe the power consumption graph, we will see just how much it changes between sleep mode and waking up. So as we can see, during the deep sleep mode, it's consuming around 10 milliamps of current. When it finally wakes up, it peaks at around 60 milliamps on average, and you can see the various stages of waking up. Now you may be wondering why it's consuming 10 milliamps when it's asleep. The answer is that it's not the microcontroller that's actually consuming that power, it's going to be the onboard regulator with the USB to UART chip. So the whole development board itself can't go to sleep, just the microcontroller. But even then, a jump from 10 milliamps to around 50 to 60 is a huge amount of current being saved when put into deep sleep mode. Another really useful thing you can do with the Power Profiler Kit 2 is to monitor the power consumed by a project and then use that to infer what it's doing. In other words, we can figure out what our microcontroller is doing based on its current consumption. And this can be a useful tool when trying to figure out if something is working correctly. In this example, we have the ESP32 and I have it connected to my Wi-Fi network. Now, if we observe the power characteristic of this device, you will see clear patterns in the power consumption as it reconnects to the Wi-Fi, does some handshaking, and confirms with the router that it is still connected. So if we go ahead and watch the live view of the current consumption of this ESP32, we can see how it's performing different tasks in the background here, going between two different main power levels, and then you suddenly get these large spikes. It is at these spikes where the ESP32 is actually sending a message to the router and then receiving. So if we stop it there, we can actually zoom in and see the major power difference between normal operation and sudden Wi-Fi communication. So it's a very, very big difference. But this can be used to confirm that our device is indeed working, or at least is working as we expect. So we do expect it to communicate with the router once every so often, and we do see that in the power signature. Now there's one more feature on the Power Profiler Kit 2 which we haven't looked at yet, and it's the 8-channel input logic analyzer, and I think this makes this quite unique. Essentially, we can connect this to different digital circuits and not only monitor the power consumption, but also monitor the different logic states. Now, when trying to come up with a really interesting project to demonstrate the logic analyzer on the Power Profiler Kit 2, I felt like I couldn't do this guy any justice, nor could I make up a really cool circuit that was actually functional and practical. But then it hit me. I've been working on a secret Z80 project that retro lovers out there will appreciate, and we're going to go ahead and connect our logic analyzer to various control pins so we can see this thing in operation. So now we've got our machine connected to the Power Profiler Kit 2. We're going to be observing two specific signals on this I/O port here, but we are going to observe the various different control signals as well. So the power is on, we are connected, the app is running. We're going to hold the reset to keep the computer from doing anything interesting. We're going to start, and then we're going to release the reset button. And as we can see, interesting stuff is happening. So here we can use this top part of the graph to zoom in and observe the logic states at different times. And this can be an extremely powerful tool when trying to debug logic circuits. Everything featured in the video, including the Power Profiler Kit 2, can be purchased from our Electromaker store, link in the description below. Thank you for watching, and I'll see you next time.